And then he says the map that sends each pair v comma w in SU2. I mean, of course, we could also look at this as what, SU2, right? Because as we discussed last time, S3 is SU2, especially with our 2x2 complex representation of the quaternions. So he said there's a homomorphism, phi, from SU2 cross SU2 to what? To the SO4, which is the rotations of R4. And the mapping is what? Phi of Q, excuse me, phi of V comma W.
It's a map.
It's a map, right? So this acting on Q is equal to V inverse QW. And we want to study that map and calculate its kernel. I'm going to ignore him for a moment. That's okay with you guys. First of all, the fact that it's on 2, right? So the theorem on page 39 gives us phi is a surjection, right? That's one thing we might notice, right? Because that says that any rotation can be written like this. So this is a homomorphism of groups also. We could prove that. Probably wouldn't hurt to do that. If I take phi of like V1 W1 times V2 W2, I get what? I get phi of what? V1 W1 V2 W2. I mean W1. Sorry, V2 W V. Words. That. Which is what? This is V1 W. God, goodness gracious. V1 V2 inverse, and I want this thing to act on Q, right? Great googly moogly. After that stupid math there. Alright, so that Q, and then what? W1, W2. But this, by sock shoes, is V2 inverse, V1 inverse, Q, W1, W2. And then we just kind of have to work our way back. This is phi of V2, W2 acting on V1 inverse Q, W1, which by the way is phi of V2, W2 acting on phi of V1, W1 acting on Q, right? Then you can strip the Q off and argue that the phi of the product is the composite of these, which is what we want to show, because the multiplication in the rotation, if we look at rotations as linear transformations, the multiplication is that of function composition, and that's what we've shown. So it is a homomorphism, right? All right, so then what? If it's a homomorphism, we can judge the injectivity of it by studying its kernel. If the kernel is just the identity, it's injective. On the other hand, if it's not, well, let's see what happens. Can I erase? I can erase here. So how do we calculate the kernel?
Find everything that maps to 1.
Right, so the kernel of phi is going to be V and W in, yeah, S3, because it's less writing. such that, sorry, phi of v comma w is equal to the identity map, right? But what does that mean? That means v inverse qw is equal to q again for all q in H, I suppose, which is our R4. So what's that give us?
Choose q equals 1.
Ah, great, yeah. Put q equals to 1. What's that tell us? That tells us v inverse w is 1, which tells us what?
E equals W.
V equals w. All right, now we go back. We've got v inverse qv is equal to q again
Mm-hmm.
for all q. So what does that tell us?
Goes back to the whole pairs of quaternions thing, doesn't it?
Maybe.
Like it. Maybe I'm thinking of something else.
You might not be wrong, actually. I think we proved. Yeah, before, didn't we prove that this and minus v?
Yeah, it's antipodal quaternions. It's like a rotation.
Right,
Yeah.
very good. Been a little. I forgot about that. Thanks. That's very useful though, because it's obvious that the identity is a solution.
Right.
So then it follows that minus identity is the only other solution.
So it's got two elements.
Right. So
Kernel.
with that thought, kernel phi is the identity and minus the identity. Minus the identity is a rotation in R4 because the determinant is still 1, because you get minus 1 times minus 1 times minus 1 times minus 1, 4 dimensions. In 3 dimensions, minus the identity is a reflection, but in 4 dimensions it's not. Weird, right? There it is. So this means that this homomorphism is a 2-to-1 map. It, there's 2 different points in here which map to 1 point in here. And you can use this to prove that SO4 is not simple, because a non-trivial subgroup of phi would be something like, if you take, say, for example, the identity matrix crossed with SU2, you can prove that that's a normal subgroup of SU2 cross SU2. So that's a non-trivial normal subgroup, and you can show that that's closed under conjugation. And then the image of this in SO4 under this homomorphism is likewise a non-trivial normal subgroup of SO4, which shows you that SO4 is not simple. That's obviously not a geometric argument. That is, it's an algebraic argument. Yeah. If you don't believe me, that if you call this thing H, right? So if you look at G inverse HG, it's stuff like what? G inverse, things like the identity matrix. My notation is kind of screwy, sorry. I'd rather just talk through it than write it. What's going to happen?
Not call it H.
What happens when you, sorry. It wasn't a double H. What happens when you conjugate here, when you conjugate by something in SU2 cross SU2, the first component and its inverse pinches the identity back to the identity. But over here, you know, the second component, well, it's again conjugation in SU2 and the second component, so it's again in SU2. So you're again back in this thing when you conjugate by something in the direct product of SU2 and SU2, which shows it's a normal subgroup. And he gives another argument, which is nice, which is that this is also equal to the kernel of, say, psi, where you have psi of v comma w equal to, what is it? V comma 1 maybe? Oops. See, because this is a homomorphism, kind of a stupid one, but it is one. And what maps to identity? Well, everything maps to the identity in the W, which is this,
Right.
and just 1 in that. So the kernel of psi is that. But if this is a homomorphism, then the kernel is a normal subgroup of the domain. So that's another way to prove, a more efficient way really to prove that this is a normal subgroup. So that discussion we had the other day about kernels being normal subgroups, it's not just idle chitter chatter. It's a calculational technique. It's much easier to exhibit a homomorphism and argue that a kernel is normal as opposed to, well, I don't know, it's the same, different notation for the same idea, but there it is. All right. I think I have 10 minutes left.
When are we supposed to go to?
Well, 5 ostensibly, but I started at 5:40, so I feel like I have till 5:10. Is that reasonable? I mean, I can go longer if you guys want me to.
No.
No, okay. You're supposed to say yes.
Get until you say like one word of chapter 3, so you can say you got to chapter 3 and then we're done.
No, it's so bad because then we have a whole week to forget the most important, like, foundational things to chapter 3.
So-
and then you build on that, and then we
Yeah.
have nothing.
I already actually talked about the discussion in chapter 2 last time a little bit, which is basically that the role of simple as it applies to Galois theory. It's very interesting. And he's very proud of the fact that there is a geometric argument for the simplicity of SO3 in this chapter. And I'm proud of it too. I just don't understand it just yet. I will come to the point of understanding it. I'm working on it. In any event, I'm going to talk to you about chapter 3 now. Chapter 3 is very, very nice stuff. So in this chapter 3, we learn how we should really look at how we should build matrix groups in sort of a more systematic algebraic method. And he mentions that this is probably due to, well, here, I shouldn't attempt the pronunciation of this name. I have a resident French scholar, I'll let him do it. Here you go.
Claude Chevalier.
There we go. Chevalier. Okay. Sounds so much more festive when you say it. That's good.
Did you say Claude?
Claude.
As Claude?
Yeah. Yeah.
Claude sounds so...
My typical English mispronunciation of this is, now you've said it right, I can't unthink it. I think I usually say Chevalier, or Chevalier. I don't know, it's wrong.
Ooh, that one's worse.
Yeah, that's right.
There might be missing an accent or something.
Missing an accent, yes. So there are 3 main spaces to look at. You've got Rn, you've got Cn, and you've also got Hn. And each one of these has a sort of notion of dot product, or let's say inner product. Rn, of course, you're familiar with, right? If we have 2 n vectors, x and y, the inner product of x and y, you know what it is. It's x transpose y. Great. Cn, well, it also has what's called a complex inner product. And the complex inner product we can also denote by x comma y. But Well, it's a little bit different. So what we have here now is x dagger, dagger, y. Now what that is, actually, is x conjugate transpose y. So this inner product is, oh,
And that's the complex.
is that right?
The complex
Do we?
conjugate.
I'm. Uno momento. Conventions and such. Give me a second here. You could go a couple different ways here on the formula. I want to make sure I'm not. Oh, so sorry.
These are their dot products.
Let's try that again. So what we're going to do is x transpose y conjugate. There we go. Oh, well, there it is.
No,
So what you're looking at here is like x1, y1 conjugate plus x2, y2 conjugate, xn, yn conjugate. And then down here, I'm less confident about what to write. I want to say, I don't know.
These are their corresponding dot products.
Yeah, these are the inner products, these spaces. Oh, it's the
That's
same.
the same thing with Wix.
Yeah, it's again x transpose quaternionic conjugate. So we're looking at like x1, y1 quaternionic conjugate and so forth. So, I mean, each one of these, of course, you could calculate the length of a vector in terms of what? You know, I mean, these are all very familiar. If you look at, for example, you know, x with x, what do you get? You get like x1 squared plus x2 squared, right?
Mm-hmm.
Plus xn squared. This one, if you look at, say, x with, maybe I should use z with z for complex n vector. You'll get like
The modulus squared.
exactly modulus is the first component of z squared plus the modulus of the second component squared and so forth all the way down to the squared nth modulus. So it's the sum of the moduli squared of the components. And the same with the quaternions down here, QQ, you're going to get, you know, the quaternionic modulus, where of course these are what? I mean, that's the sum of the, if you look at the quaternions in real notation, this one might be, say, like a1 squared plus b1 squared plus c1 squared plus d1 squared, and so forth. If you break it down to real notation, there are 4n squared terms there. If you break this down into real notation, you've got something like x1 squared plus y1 squared. Right, you've got 2n squared terms in the complex case.
5:00 p.m.
Silence. Yes, bueno. So, each of these inner products, you can study what are called the isometries. You can study what's the definition. An isometry of, which is, let's say, a mapping from, you know, K cross K to, I don't know, I guess it's always in the complexes, right? Yeah, it's always in the complexes, isn't that right? Oh, no, I think it's always, in K, generally speaking. These don't have to be real.
Okay. Right.
What is okay? This is any of those three.
Okay, yeah, any of these three. is a linear transformation. Now this is not the most logically primary definition. I mean, you could study the notion of isometry and then prove that they have to be linear. I'm not really interested in that question at the moment, so perhaps I should say a linear isometry. You know, is a linear transformation. And oopsie, what do I want here? I want Kn. Let's say T, such that you map Kn to Kn. And
Is it
you have the following. You have T of x, T of y is equal to xy for all x and y and Kn. What is it really?
this is Kn cross Kn mapping to K, right?
Yeah.
So it's not Kn.
No. It's an inner product. Its output's a scalar.
Right.
That scalar might be a real number, a complex number, or a quaternion in our generality at the moment.
That would make quaternions numbers.
Yes, quaternions are usually thought of as numbers. As we've discussed, I'm slightly more open-minded about what a number is. Maybe too open-minded. I don't know. Now, it turns out that if the determinant, so I guess you could define some kind of universal notation for all of these. You could say that the set of all this means T is an element of like the orthogonal transformations on n dimensions over K. You could do something like that. And then you could say that if the determinant of T is also equal to 1, then T is an element of SON K. I don't know if that's terribly useful, because really we're interested in the substructure here more than, we make arguments for each one of these cases separately, okay, like a lot of times. So first of all, Rn. If you have, check this out, if you have, so let's let T of x equals to Rx. All right? So we have Rx, comma, Ry equal to xy for all x and y, right? So what's that give us? That gives us Rx quantity transpose, Ry, which is x transpose, Ry, R transpose Ry. On the flip side, we have x transpose y. But if you tilt your head and squint there, you can see that there's clearly an identity matrix right there. Now, if you studied your linear algebra, you know that this being true for all x and y implies that this matrix is equal to that matrix. So in other words, O and R, which we usually just say ON, is R such that R transpose R is equal to the identity matrix. My beloved orthogonal matrices over the reals. I took the geometry out of it. No reflections here, just matrix algebra. Sorry.
And that's just the reals.
Just the reals, right? And then if we add the determinant 1 condition, we get SON, which are the rotations. If we study the determinant, right, the determinant of R transpose R equal to I is what? Well, that's the determinant of R quantity squared by properties of the determinant. But in terms of real solutions, you got plus or minus 1 there. So you either have rotations or reflections. In fact, you can prove that ON is in fact like SON union with what you might call minus SON. What happens when you do the same calculation over the complexes? Well, traditionally we use a U in that case. Now at this point, it's erasing is going to become too much trouble. Start from scratch. So for all x and y complex n vectors, so what is this? This is, by our definition, ux quantity transpose.
Y conjugate.
Yeah. Equals to x transpose y conjugate. Alright, Sachs-Hughes property gives me x transpose u transpose u conjugate y. By the way, complex conjugation doesn't have Sachs-Hughes property, just like that. Oh, y conjugate. X transpose y conjugate. But this implies what? This implies that u transpose times u conjugate is equal to what?
Identity.
The identity matrix, right? Which is not what I wanted to see. Curious. I think we can fix that. Quote unquote fix it.
Take the conjugate of both sides.
Take the conjugate of both. I think you got it. So take the conjugate of both sides. I think it's sort of the standard presentation. So conjugate gives me u conjugate transpose, u conjugate conjugate, which is just u. I conjugate is I again. In other words, what we get is the u dagger Hermitian conjugate is what it's called, which I use a dagger for sometimes. Let's see, it's a dagger. Yeah, whatever. This symbol's getting too complicated.
Deception.
That is what's called a unitary matrix. So the isometries of the complex inner product are precisely the unitary matrices. Solutions to u dagger u equals to the identity matrix. If we add the additional condition that the determinant's 1, then we get SUN, the special unitary group of order n. Okay. So next time I will go through the details of the next one, which is the quaternionic inner product. That one, when you run through the details, what you end up defining is known as the symplectic. The symplectic matrices preserve the quaternionic inner product. And so those three families of matrix groups, the real orthogonal, the special orthogonal real matrices, the unitary complex matrices, and then the symplectic matrices built over the quaternions. These are the main players in the study of matrix groups and the algebras. Most everything we're interested in can be built from these three families of things. And so it's so interesting that all three of these families of things arise as simple, just linear isometries of these inner products. To me, it's very beautiful. Now, the rest of chapter 3 is about, of course, like the details I've been showing you about that, but also discussions of the so-called path, how are these matrix groups connected in the topological sense or not? And also, more interestingly, these so-called maximal tori. There's like a torus hidden in these matrix groups. This maximal abelian subgroup that commutes with everything else in the group, or with itself, I guess. And so you find these maximal tori, and then you can use that to calculate the center of the group. Now the center of a group is the set of all elements in a group that commutes with everything else in the group. But once you know the tori, you can calculate the center pretty simply. Not meant in the technical sense of simple, but sorry, it cracks me up. And apparently that calculation goes all the way back to Weil, which I'm probably mispronouncing. No, it's Weil. It's the German. It's not Way. It's the other one. So Weil in 1925. Weil's a very pivotal character in this whole story. Anyway, that's where we're going. Chapter 3, I will hopefully...
If it's German, it's Weil.
Yeah, Weil. That's right. So I'll try to put the finishing blows to chapter 3 next time. And who knows, maybe I'll actually understand the geometric proof of SO3 being simple by next week. Who knows, we'll see. The story, it remains to be seen. Maybe one of you guys will understand it completely and explain it to me. We shall see.
Yeah. Or the proof that every isometry is most in reflection.
Yeah. Oh, that one. Oh man, why did you have to remind me about that? I could have got, if I had forgotten that I didn't know that, then I could have just said, oh, we did that today, so it's done. But you're right, it wasn't really done today. And then the even harder thing, how do you find the explicit isomorphism or homomorphism between the, I guess it's got to be a homomorphism between the, homomorphism, obviously, between, what was it, SU2 and SO3.
Right, so that's still standing as homework.
That's
We have
that's
stuff
a
on-
homework that may take us more than 1 week to do.
we
The
have
stuff on
17.
page 17 and 18 you guys can finish. That won't be
Right.
too onerous.
And that's it for this week, or this? It's not something else?
That's it. If you want to start fiddling around with chapter 3 homework, if you have time, go for it. Otherwise, I'll assign those probably next time. Sound good?
Yep.
Excellent. I mean, excellent.
Any small talk you want to get on camera before I turn it off?